Hi Web3D, welcome to the presentation on VIA, Visibility Aware Web-Based Virtual Reality. I'm Slocum and I'll be giving the presentation. I'm a fourth year PhD student at the University of California, Riverside, and I worked on this paper with Jingwen Huang, the second year undergrad, and Professor Jiasi Chen, both of our advisors. So to overview the presentation, we're going to quickly cover some background information in order to understand VIA. Then we will go into the main problem that VIA solves, the causes, and how we came about the solutions. We will then do a quick demo of VIA in action, and then we will go into the experiments we ran in order to evaluate VIA, and those results quickly finish with a Q&A session. So to start with the background, VIA came about as an idea when poking around the WebXR framework. This is where we get the web-based virtual reality component of the presentation. WebXR is a framework built on top of Web3D, which is designed to enable VR and AR on the web. WebXR uses a technology known as the GLTF format in order to transfer the graphics information over the web. The GLTF is a JSON-like file object which contains metadata about the geometry and the textures of a scene. The geometry is typically stored in a .bin file along with other information like animation, and the textures are mostly stored in really common image formats like PNG and JPEG. So the main problem that we encountered when working with WebXR is incredibly long loading times on mobile devices like phones or headsets. These loading times could take anywhere from 30 seconds to multiple minutes on incredibly slow networks. The download sequence of these objects is similar to how you would request images and JavaScript and text on a normal web browser, but in this case it's more complicated, much larger because they are full 3D scenes. The main causes that we could find for this problem are the first being that all the geometry and animation data are stored in one large .binary file. In some cases, this binary file can be larger than all other files requested by the website. And this must be downloaded before any objects can be rendered in the headset or on the web browser. Typically just one of these and many image files. The image files can be bigger than the binary, but in some cases the binary is so monolithic it dwarfs them. The second cause that we could find is the fact that all of these images are requested in arbitrary order, typically whatever order is decided by the 3D modeling software that generates the GLTF in the first place. So for example, here we have a user who's standing on a balcony of a shack looking at a satellite dish on top of a mobile home next to them. The roof above the shack, which is not visible to the user, is requested about 6th over all of the 50 objects that could be requested, and the satellite dish's texture is not requested until about the 47th. So the user is staring at an incorrect image for an incredibly long time while other objects that aren't necessary are being loaded behind them. So our general approach for solving these two causes, and by extension the problem, is to divide up the binary and to begin prioritizing the objects and their associated textures by whether or not they are in view. So to go into more detail, the way that your typical WebGL and WebXR scene is loaded is you have you first request the GLTF file, and then the GLTF begins requesting the binary, and the image is in arbitrary order. So for example, we have a scene here where we have the satellite object that is in view, and the ground object, which is the rocks and grass around the user that they can't actually see because it's behind them. So both of these objects have their geometry data stored in one binary file, so at time equals 1, that gets requested first. It's a very large file, it takes a long time to download. Then, because the texture fetching is arbitrary in order, the rock texture for the ground object gets downloaded, and then the moss texture for the ground object. And now we have all of the dependencies for the ground object downloaded, we can begin rendering it, but the issue is the user isn't looking at them. So this doesn't help us make a correct image any faster than downloading things arbitrarily. The satellite object then is fetched, but much later, so the initial view that you look at is completely incorrect. Our approach starts with splitting up this gigantic binary file into much smaller ones, one for each object. The satellite object is in view and is prioritized, so the binary for the geometry of the satellite object is downloaded first at time equals 1, and then the texture for that satellite object is fetched without downloading any further geometry data for other objects. At this point, we can begin rendering the satellite object, which is in view, giving the viewer a much faster, correct view. We can then go about downloading the binary and the images for all the other objects that are not yet in view, in case we need them later. So the splitting of the binary is relatively self-explanatory. You figure out what byte ranges correspond to what objects, partition that into many binaries, maybe do a little bit extra to make sure that the byte alignment is maintained, but otherwise it's relatively straightforward. The more complicated part is prioritizing these objects based on the initial view, and we had to come up with several heuristics in order to make sure that the prioritization of these, the download order of the objects was correct. So the first heuristic we could come up with was a simple view frustum culling. We parse through all of the objects, come up with axis-aligned bounding boxes that cover those objects, and quickly get rid of all the objects that do not intersect with the view frustum. That way we make sure that we never prioritize downloading an object that can't be in view. The second heuristic that we came up with was when we had the idea of, well, if we download all the objects that are in view first, that's great, but what about all the objects that aren't in view yet? Which one should we prioritize over others? And the general idea behind the second heuristic was objects that are closer to the center of the field of view are more likely to become visible than the ones that are further away. So we assign a simple look at rotation penalty. How far would a user wearing a headset need to move their head in order to see the object that's out of view, and penalize it based on how large that rotation is. We then combine these two heuristics into a final score and use that to sort the object requests. So the general overview of VIA can be broken up into two main components, an object scoring component and a partitioning component. The object scoring component will take as input the scene metadata file, or the .gltf file, and the user's initial positions and orientation for their first view. We will take the metadata file and come up with the axis-aligned bounding boxes by parsing that. We will then perform the rotation and view frustum culling scoring algorithms using the initial position and orientation of the user, combine those two to get our final heuristic. The second component of VIA is the data buffer grouping, or binary partitioning, where we take in the same metadata file, but also the binary file containing all the data buffers, and begin grouping them based on what meshes correspond to what parts of the binary, and then split them and come up with new metadata files and new binary files. All these are output in order of the object scoring. So the typical output looks like a large amount of GLTF and binary files that are sorted in order that they would be downloaded off the server when the client connects. We're going to now go forward for a quick demo. Okay, so for this demo we have WebXR running in Google Chrome. I am on a wired connection, but I am throttling the network to about 50 megabits per second, which is way faster than most mobile networks, but for the sake of time we do need these things to load in a reasonable time for the presentation. Alright, so we're going to quickly load a control scene just to show how this typically works. I do have the network log on the right side. So this is an indoor house scene. The skybox and the JavaScript and the GLTF load first. We are now loading all the geometry data, and as soon as it's done, it all appears at once. It takes many seconds for this geometry data to be downloaded, and by the time it has been downloaded, all the images have been downloaded and everything can just immediately render. But it does take many seconds for all of this downloading to occur. Now if we run the VIA adjusted version of the same scene, we see that the floor and the bed and the sink immediately appear. The walls load in a little bit later, and now we're continuing to load in all the other scenes that are all the other rooms that are not currently visible, but this room and all the objects visible were loaded far faster than the control. So now we're going to move on to the experiments that we designed in order to evaluate VIA and the results of those experiments. So we had 5 different test scenes that we selected for varying sizes, and not just varying sizes, but ratios of what types of data within that size. So some scenes where the geometry data was incredibly large and the images were small, and some where that was flipped, and some where they were about the same size. We also chose scenes that had similar spatial arrangements and not similar spatial arrangements. So some that were completely enclosed, some that were open, some that were urban areas, some much more chaotic, and some without floors like a solar system. All 5 of these test cases we ran through all 3 of the systems. So we have the control where there are no changes to the binary, no change to the GLTF, no change to the images. The order is whatever the arbitrary order we got it from. Then we have VIA, where we split up the binary and we prioritize the images in the object ordering in order to see if it will go faster. And then we have VIA image, which, if you recall, VIA has 2 components. VIA image is simply VIA, but without the binary splitting component. So we just reorder the images based on visibility, and we leave the binary as its original monolith. We take all of these test cases and we run them on 3 different network bandwidths and round-trip times that are covering typical mobile network conditions. Our main finding was that VIA strictly has lower latency, that is the time from the point at which the page loads to the first frame that is correctly rendered. VIA always has strictly lower time than the control. This time is even further better on slower networks. Very occasionally, VIA image will have about the same benefits as VIA, but most of the time it performs about the same as the control because both VIA image and the control require the entire monolithic binary to be downloaded before anything can be rendered. So when we looked at the different network conditions, we discovered that VIA's performance over the control does depend slightly on network conditions. Typically, the slower and worse your connection, the better VIA will perform when compared to the control. The only trade-off really for VIA is that VIA introduces extra round-trip times for resource requests. If you have one gigantic binary file in order to download all of the geometry, you only have to send one round-trip time request in order to get that file to start downloading. But if you split it up into like 400 files, you now have 400 round-trip times that you need to account for. Typically, this is an incredibly short amount of time, measured in milliseconds, so on slow connections, it's almost always worth it to split up the binary. The main variable that will change how well VIA performs over the control is what initial view you choose within the scene. We ran an experiment on one of the test scenes on one of the network conditions to see how a different view would affect the latency, and found that it's incredibly important. We ran an initial view where only a tree, its leaves, and the ground immediately surrounding the tree was visible within the initial view. So we had to download 3 objects out of 423 and had incredibly faster results than the control. We also ran an experiment where every single object was visible and saw that the latency was about the same, which is what we expected. Somewhere in the middle, you get middling results, of course. One of the main things that occurs when you're wearing a headset and you're loading into these images is that you have a camera that's attached to your head, and it takes some time for the scene to download. So by the time that the scene is done downloading, your head may have shifted, you have shifted your weight, tilted your head to the side, and the initial view estimate that the download started with may be different from the initial view after it's done downloading. So we ran an experiment to see how well VIA performs if the initial view is slightly off from where we expected it to be. Just simply rotating the user's head in 15-degree increments and measuring the change in latency, we discovered that VIA continues to outperform the control until you look more than 90 degrees away from the initial orientation, at which point VIA begins penalizing objects more than the control would. So as long as the user is looking generally in the direction they were originally, VIA continues to outperform. So I'd like to thank you for attending this talk once again and ask for any questions.